Hello, everyone. Thanks for coming. My name is Timur. I'm a C++ developer, and I'm specializing in audio and music technology, and I work for a company called Roly, based in London. And we do lots of different music technologies, and one of the things we do is Juice, which is the logo on my t-shirt here, which is a cross-platform C++ framework, which you can use to build any kinds of apps, but it has a focus on audio apps. So this is sort of my background. And first of all, a disclaimer. As you can probably hear, English is not my native language. And also, I'm a bit jet-lagged, so I apologize for that. So I hope you can still understand me. And another disclaimer, this is an introduction talk. So I'm going to be talking about Lockfree programming, modern C++. And this is a basic introduction talk. So if you are already an experienced developer and you've already done some Lockfree programming before, you're probably not going to hear anything new apart from maybe a few bits about C++ 17. So sorry for that. Can I just get a show of hands who has done some Lockfree programming before? OK. So well, maybe there's going to be a few new bits, but mostly it's going to be really a basic introduction talk. So that's what it is about. And also, I'm not going to mention any platform-specific things. So this is really about standard C++. So I'm not going to go into any details about specific hardware architectures or anything like that. So all the code I'm going to be showing is going to work on every platform as long as you have a compliant compiler. So here's the overview, what we're going to do. I'm going to start with a little bit of motivation, why you would even do Lockfree programming in the first place. Define a few useful things, like what does it even mean, Lockfree, a few useful definitions. Then we're going to look at the interface of std atomic, because this is really the most important tool that C++ gives you for Lockfree programming. So we're going to go through the whole interface and make sure that we're all on the same level of how it works. Then I'm going to talk a little bit about how you can use that to exchange values between different threads. And then we're going to get to the really fun part of the talk, which is implementing a Lockfree queue. What I'm going to do is I'm going to implement, with you, I'm going to implement the whole thing from scratch. So this is really the fun bit, and I hope you're going to stay awake until then. So let's dive in. So what's the fundamental problem that we're trying to solve here? It's really, we have multiple threads exchanging data as they keep running. So I'm not going to talk about things like futures and promises, which is basically if a thread is finished to get that back into another thread. It's all about threads that keep running and have to exchange data while they do so. And if you have multiple threads, as you all know, you have to synchronize the data access. As long as threads are reading data, it's usually not a problem. But as soon as one of the threads is writing, you can have race conditions, so you need to synchronize that. So I'm sure everyone's familiar with the concept of race condition, but we're going to have like the exact definition of it in C++. So if you want to do this, then the main tool really, the main approach to fix race conditions are things like locks, critical sections, semaphores, and condition variables, and of course some higher level facilities that are built on top of those. And modern C++ really has a lot of those facilities. So since C++ 11, we have std mutex, we have std recursive mutex, we have timed mutex, we have a lock guard, which is useful to make it a bit safer. You have a unique lock, which is a bit more flexible, and you have a std condition variable, which is another way of exchanging data between threads. And then bits keep getting added to it, so it keeps getting better. And since C++ 14, we have the std shared lock, and then C++ 17, as Nico was describing in his wonderful workshop yesterday, we're going to get the shared mutex, and we're going to get scoped lock, which is basically the variadic version of the lock guard. So that's great. And I think most programmers really should focus on mastering those things. However, if you want to do Lockfree programming, we're going to take a different approach. And I think the simplest definition of Lockfree programming is really we don't use any of those stuff. Instead, any of those things. Instead, we're going to achieve our synchronization in a different way. Now the question is why you would even bother doing Lockfree programming, because most people agree that it's very hard to do. Hopefully I can convince you that it's actually not that hard most of the time. It's hard to write, it's hard to maintain, and often the overall performance that you get is actually not better. Sometimes it is, sometimes it's not. It really depends on your use case. So why would you even bother doing that? And the answer is that if you have mutexes and locks, basically you have something like this. Yeah? So actually, we're in England, so I should have flipped the image around. Sorry for not doing that. But yeah, mutex is basically something like this. You have like different threads, so it's like an intersection, and a mutex is like a traffic light, which says, if it's green, you're good to go. If it's red, you have to wait for the other one, and then at some point, it's going to turn green, and then you can continue. A lot of the time, this is good. Sometimes you're waiting on a red light, even if there's actually no other cars on the other street. So that could be a performance problem. But really, the main reason why you want to do Lockfree programming is if you can't afford to wait on a red traffic light, like, for example, the ambulance car down here. The ambulance car really has to get as fast as possible to its destination because human lives could depend on it, right? So it just it can't afford to just stop in the red traffic light and wait until all the other cars are done and the traffic light turns green. So you can't really afford that. And where does it happen in code? Typically, whenever you have something like a real-time environment, which basically means one or more of your threads are under strict time constraints. They're doing some work which has to be finished as fast as possible, or it has to be finished in a certain amount of time. And blocking and waiting for a mutex is not possible because you simply don't have time for it. So it means in a thread like this, you can't use any locks. You can't do things like allocating, deallocating memory because that's also a blocking operation. And you can't really call into any third-party code either because you don't know if it's lock-free. You don't know how long it's going to take. If you have a third-party API, people don't document things like, well, this function is guaranteed to finish within X milliseconds or whatever. Actually, C++ doesn't even have a way to express that. Some languages do, but C++ is not one of them. And why can't you do any of those things? Well, because if you're blocking and waiting on something, then there's no guarantee how long you will be waiting, because maybe you don't know what code you're waiting for. Also, if you do that, if you're waiting for other threads, you're at the mercy of the thread scheduler of your operating system. And you don't want to rely on that, maybe. And this also brings with it some other problems, like priority inversion, which basically means if you have a high-priority thread and it's waiting on a mutex that is owned by another thread, which is low priority, then that other thread that you're waiting for has low priority, so the operating system can decide, hey, let's just, instead of executing that thread, let's execute some third thread, which you have nothing to do with. And then you're going to be waiting for that. So your high-priority thread is going to turn into a low-priority thread, effectively. And then you're going to suffer from a lot of problems. And you're not going to finish your work in time, and that could result into a system failure. So this is the kind of cases that we're talking about. And typically this happens, so these real-time environments, they come up in all kinds of different fields. They come up in audio processing, which I only put first because this is my field. But you also have problems like this in finance, in embedded systems, and lots of science and engineering problems. So let me just give you a few examples. For example, in audio processing, what we have is you have a sound card, and the sound card has a little crystal in it, which is like a timer, and it's going to call you with a callback on a high-priority system thread regularly. So maybe every millisecond or so, you're going to get a callback from the sound card, and you're going to get like a buffer of floats, and the sound card's going to say, fill that buffer with floats, and then it's going to send those floats to the speakers. And that callback is going to get called regularly. And if you're not finished with filling the buffer with numbers in that millisecond, or like by the time the next callback hits you, then the data is going to be sent to the speakers. It's going to be garbage data. And then what you're going to hear is you're going to get an audible like audio glitch. So you're going to get something like in your speakers, right? And this is bad. For example, if you're this guy and you're playing something in front of 1,000 people and you have some audio code going on your laptop, and then you're going to get into this situation, then first of all, you can blow the speakers, and second of all, everyone's going to turn deaf. So that's something that you never want to happen. If you're interested in audio processing, I gave another talk a couple of years ago at CPPCon about specifically that. It's called C++ in the audio industry. So if you're interested, check that out. But this is not an audio talk. So of course, the same situation or similar situations also occur in other industries. For example, in finance. And the most extreme example of that is, I guess, high-frequency trading, where typically you have some kind of hot path where you need to take a decision very quickly, like what are you going to do with the given trade, for example. And if you're in that thread, you have to make an immediate decision, and every microsecond counts. And if you're late by a few microseconds, it's going to cost you a lot of money, so you can't really afford to wait on a mutex. And if in that hot path, at some point you need some data that's shared with another thread, well, at some point you're probably going to look into log-free programming at some point. Another area is science and engineering. For example, if you have those robot walkers here, and imagine your C++ code controls, the motors in those legs, and then they're going to need to know what to do with a very high frequency. They need to get some updates on how to move around. And if the motor in the left leg is not going to get an update on what to do for too long because you're waiting on a mutex, then this is going to happen. And I'm pretty sure the person sitting in that cockpit is not going to appreciate that very much. So really, what you want to be doing is, instead of doing this, you're going to have to arrange your traffic in something like that, where instead of traffic lights, you're going to have ways of the traffic lanes sort of like merging into one another so that all the cars can keep going and none of the cars have to slow down. By the way, I shamelessly stole this picture from a talk by Herb Sutter. Thanks, Herb. It's a great talk where he talks about, his talk is called Juggling Razor Blades. It's a great talk. I really recommend you watch it. He has some very deep explanations. And he implements in that talk a log-free linked list, which is I'm not going to do here. But yeah, watch his talk. It's a great talk. Coming back to this, I think it's a great analogy. Because this setup can guarantee that your cars always keep moving. Well, then, of course, you have different ways of how do you merge traffic into one another, and what does it actually mean the cars always keep moving? So here we can make an important distinction. There's actually two different kinds of log-free guarantees. One of them is log-free, which means at least one thread would always make progress, which you can imagine if you have a traffic lane and traffic is merging in there, then either this car is going to wait a little bit until the next slot is free, or this car is just going to go and then there's going to be another one. But you always have to guarantee that at least one thread will always make progress. And then the stronger version of that is the wait-free, which means that every thread at every point of time will keep making progress. So no thread is ever going to wait for any other thread. And the good thing, regardless of whether you have log-free or wait-free, the other good thing about this is that you can never deadlock. So actually, even if you're not in a real-time environment, if you have one of those two guarantees, it can be a good way to reduce contention, to get better concurrency and scalability, even in non-real-time systems. But if that's your use case, I think you should really benchmark the code before you put log-free algorithms in production code, because it may turn out that it's actually not having better performance. OK, so before C++ 11, C++ didn't actually have any notion of threads, right? But now we do. Since C++ 11, we have a memory model and a standard. And I'm just going to display a quote from the standard. This quote mentions bit fields. Those are those weird things where you say int x : 5 or whatever. Anyone here using bit fields? OK, 2 people. So I think it's a bit of an obscure feature that most people don't really need, so we're going to just gray that out. So the standard says a memory location is an object of scalar type, which, by the way, means one of the built-in numeric types or a pointer or an enum. So that's a memory location. And 2 or more threads of execution can update and access separate memory locations without interfering with each other. So that's really the main sentence from the standard on the memory model. And what's important about this is what happens if you inverse the statement. If 2 or more threads can update and access the same memory location, that's called a data race, and then you get undefined behavior. And that means if you're modifying a value from one thread, then the other thread can see a value before the write, after the write, some garbage value which represents something in between, or actually your code can do something completely different, and your computer can blow up and catch fire, and that's going to be consistent with the standard. And the reason it's undefined behavior is because optimizers can rearrange your code, right? They can reorder instructions, they can optimize variables out of existence, they can optimize memory accesses away, they can reuse one memory location for 2 different variables, and optimizers can do all kinds of crazy stuff. And the way they do it is the optimizer is always going to assume, when doing these optimizations, is that you don't have a data race in your code. And if you do, then no one knows what the optimizer is going to come up with. It garble your code, and you can get some really weird behavior. By the way, declaring something as volatile is not a way to fix this. It's something completely different. People have done that in the past. Maybe people are still doing that. I don't know. But volatile has nothing to do with this. It's a very different thing. And it's still going to be undefined behavior. So one way to fix this so there's actually just 2 ways to fix this. You can have either locks or you can have atomics. And now we can come up with another definition of Lockfree programming. If you have, let's say you have a chunk of code, it doesn't really matter what that is, and there's a race condition in there. Normally what you can do is you can put a lock there, and then it's safe. Now, probably all of you know that now here the lock is protecting the whole function, and I guess all of you know is that this is not really good programming practice, and what you really want to do is you want to put the lock just around the piece of code that actually accesses the data. Yeah? So you want to make the scope of that lock as small as possible, because then you get better concurrency and better performance. And now Lockfree programming, or like one way of looking at this, is you reduce the scope of that lock even further until it protects just a single instruction. And when you get to that point, you just replace the lock and this one single instruction with an atomic instruction, which means, and you can get rid of the lock. And atomic instructions means that it's going to be memory access that's supported on the hardware level. So your processor has special instructions that it can do to read or write from memory with a single instruction, and that instruction is going to be race-free even without a lock. So that's a hardware feature. And every other thread is going to see either the value before the write or the value after the write, but nothing in between, and it's defined behavior, even without a lock. And doing this kind of stuff used to be really hard, because you have Intel, ARM, PowerPC, all these different platforms, and they all have different instructions with different rules. And actually, those different processors also have different memory models. So there's cases where on ARM you would need to insert a memory fence, and on Intel you don't have to do that, and things like that. And this is really scary stuff. So in order to do that, you need to be basically an expert for your hardware architecture. If you want to know more, there's another talk by Herb Sutter, which is called Atomic Weapons, I think. That's a great talk where he goes, it's a 3-hour talk where he goes through all these hardware differences on different hardware. So if you're interested in that, watch this talk. But of course, what we do as library developers is you want to hide all that complexity behind a cross-platform interface. So people started writing cross-platform wrappers for this stuff. So Qt has QAtomic int. Then one of my previous jobs, I was working for another music tech company called Native Instruments in Berlin, and I was maintaining their application framework, and they also had a wrapper for it, as I'm sure dozens of other companies had. And actually in Juice, we also have a wrapper, Juice Atomic. But since C++ 11, this is all obsolete, because now we have a wrapper in the standard, which is called standard-atomic. And standard-atomic is a type in the standard that is inherently race-free, which means that you can read and write from an atomic variable without any locks, and it's defined behavior, and it's guaranteed race-free. And actually, it's the only type in C++ that has this property. And in the next minutes, I'm going to go through the whole interface of this class, because it's so important for the rest of the talk, just to make sure that we cover everything we need. So if you already know standard-atomic very well, you can have a little break. So this is just a screenshot from CPP reference. So what we have is we have a generic template, which is the first one, which is going to compile for any class T which is trivially copyable. And then we have a specialization for integrals and for bools, and then we have another specialization for pointers. Note that there is no specialization for float and double. I'm going to come back to that a bit later. So first of all, of course, we have a default constructor for that. it's a bit nasty because it's actually not going to initialize. So atomic is like an atomic wrapper around the type t, so for example, an int. And this is not going to initialize the value. So it's going to leave it uninitialized. Yeah, you have to know that. So maybe it's better to use this other constructor to just initialize the value immediately. And there's no other constructor. So atomic is not copyable, not movable. And then basically it has these 5 member functions. So you have store, which means you can write a value into the atomic. You have load, which means you can read it. Then there's exchange, which basically means you're going to basically swap the current value with a new value. So it's going to set it to the new value, and it's going to return the old value. So it's like an atomic swap. And then the last one is compare exchange, which basically means you're going to compare it. So you have an expected value, and if the current value is equal to the expected value, you're going to set it to the desired value, and then it's going to return true. And if it's not the expected value, it's going to do nothing, and it's going to return false. And it comes in 2 flavors, strong and weak. And basically, the difference between them is that if the current value is the expected value, then strong is guaranteed to succeed, whereas weak can spuriously fail. And basically, the coding rule here is that whenever you just want to do it once, you should use the strong one. And whenever you have to do it in a loop anyway, so you're going to keep checking repeatedly anyway, then you should use weak, because then it gives you better performance on some architectures. One more thing about this. So store has a shorthand notation where you can just use an overloaded assignment operator, and equally load. There's a shorthand notation for that as well, where it has an overloaded operator t. But I actually discourage using those shorthands because I really like readable, clear code that expresses the intent of the author to the reader. And so I prefer to always use store and load instead of the shorthand, because then it makes it obvious that you're dealing with an atomic value here. So I'm actually discouraging using the shorthand just for clarity. But they're doing the same thing. So one more thing about the compare exchange ones. So basically, I think those are really the most important ones, because those allow you to, the compare exchange allows you to write all these Lockfree algorithms. And the reason why they're so powerful is that in Lockfree code, a lot of the time you run into this problem, where, for example, here it's like a piece of some Lockfree algorithm where maybe you have an atomic pointer, like a read position that points somewhere, and you want to check if you're allowed to read. And if so, you want to increment that thing. And the problem with this code is this gap, right? So you check, am I allowed to do something to that thing? And then you do it, but in this gap in between, everything can happen. You don't know what's going to happen there. And you can't put a lock around this, right? So by the time you get to the second line, maybe the condition would have changed, and you don't know, and you can't put a lock around it. So compare exchange gives you a way to solve this, and then you would write the code like this. So basically, you load the current position, and then you check if the current position is OK, and then if not, you just return. And if it is OK, then you calculate the new value, and then you say, OK, if it's still OK, if I'm still the thread that gets to modify this thing, then do the compare exchange, right? So if it's still the old value, which basically means no other thread has changed the value in the meantime, I'm the thread who's going to change this value, then do the compare exchange. If it's expected, change it to the new one. And this is really a very important pattern that you're going to see over and over again. And then we have, in Atomic, we have the template specializations for integers and pointers. And basically what they give you is those additional functions where you can atomically increment and decrement the value. That's, for example, used if you look into the implementation of the shared pointer. It has a reference count. So that's going to be an atomic reference count. And it's going to use the atomic increment to increment that reference count in a thread-safe way. And then it has these plus equals, minus equals operators, which are all atomic. And then it has these fetch, add, fetch, subtract ones, where you can add and subtract and or the current value. And the cool thing about them is it's going to also return the previous value. So again, it's useful if you're using that in log-free algorithms. So that's only for integer and pointer specializations. So as I already said, there's no specializations for floats and doubles. Actually, at the last standard committee meeting in Kona, we discussed a proposal in the library evolution group like this one, P0020, where they're proposing an atomic float specialization. It didn't get into C++ 17, but I think there's a good chance it's going to be in C++ 20, so I hope it's going to add kind of a reasonable, clean way of dealing with this. But as long as it's not in the standard, we don't have that. So basically, if you're dealing with atomic floats, you don't have operator plus, minus, plus equals, minus equals, and so on. You do have store and load, which you can use, which is fine. And you do also have compare exchange. But it's not really meaningful for floats. And I would discourage using compare exchange for floats. And the reason is, first of all, floating point comparison, as you all know, is not really meaningful anyway. But actually, compare exchange is even worse, because the definition of stood atomic in the standard says that the comparison is always going to be bitwise. And that's also what's happening in the hardware. It's always going to be a bitwise comparison, because that's how these atomic compare exchange operations work. And this means if you have a float, you have situations like, if you look at the bit representation of a float, you have, for example, plus and minus 0, right? Which is it's the same value. If you compare plus and minus 0 with normal floats, it's going to compare equal, but they have different bitwise representations. Like if you multiply minus 1 by 0, you're going to get the minus 0 one. And if you do a compare exchange, plus 0 and minus 0 are going to compare as not equal. So it's really nasty, and I don't really have a use case for compare exchange for floats. But as long as you just use store and load, you're fine. And basically, we're going to do that later as well. Yes, there's a question?
Would compare exchange be OK with even with floats if you use this pattern where you first load the old value and then you compute what the new value should be, and then you update conditionally on the condition that the old value is still there? If you read it and you compare it to what you just read, they probably should be bit for bit equal. Is that currently by the standard?
Should I repeat questions for the recording? So the question was, if you only use compare exchange for floats in this pattern where you only read the store like the old value, and then you're going to check if it changed, is that fine? I guess it's fine, but I would probably not do it. Just because if you see a compare exchange for floats, then maybe people can start using it for different things, for other things, and then it's going to blow up. So I guess it would be fine in that specific use case, but I think it's safer to say just don't use it. Because you might then change your code and then do something else, and then it's going to break. It's just dangerous.
Just staying on the topic of compare exchange. So we have a compare exchange and we compare exchange weak. Now, what is the actual difference, and why can't it just be compare exchange and let the compiler decide on the in the optimization which actual assembly to call based on whether it's in an if statement or in a loop?
So the question was why we have compare exchange weak and strong, and why don't we let the optimizer decide which one to pick? I don't really have a good answer. I think like a lot of frameworks, they don't actually have this distinction. The standard has. So it's going to be different instructions on some hardware. I think on Intel, it's probably going to be the same instruction anyway. Yeah, that's like hardware details. I'm not sure. I guess it's to give you a little bit of flexibility where you can tell the compiler, basically, now I really don't care if it fails in this particular algorithm, so it can generate faster code on some architectures. It's maybe like a hint to the optimizer in a way.
I mean, it's because it does the same thing, so...
Well, it does not do the same thing because weak is allowed to spuriously fail even if the value is the expected one. So they actually do have different behavior. In practice, it's going to be the same thing on most platforms I'm aware of.
So is it fair to say that strong is just more robust?
Strong?
Potentially slower,
Yeah,
but more robust.
exactly. So strong is always going to do what it's advertised to do. And weak does not have that guarantee, but it might be faster on some platforms, and I'm pretty sure Intel is not one of those platforms.
Might not the answer to the question simply be, we do know
Yeah. So
notoriously fail or not, and the compiler does not. So we need two different.
yeah, exactly. So that's exactly how you use it. So whenever you don't care if it fails this one time around, which typically happens if you call this thing in a loop, then you expect it to fail several times because of the way your algorithm is designed. You expect it to fail. So you call it in a loop until it doesn't fail anymore, and then you continue. And in this situation, you use weak because you expect it to fail. So you say, OK, now we allow it to fail even spuriously, and then you can get a little bit of performance out of it. So it depends on your algorithm. Like, if your algorithm says it's OK to fail because you're going to repeatedly check it anyway, then use the weak one. And if you really want to know it now, is it like expected or not, and you're doing it only once, then you should, and you just take like a different code path depending on that one call, then you use the strong one. Does that answer the question? OK. One more thing about atomics is there's actually, people confuse the terms atomic and lock-free. And those actually don't mean the same thing. So what atomic means is it's an operation that's thread safe, where every other thread is going to see the result either before it or after it. There's nothing, it's never going to see like anything in between, and it's thread safe. You don't have to put a lock around it. That's what atomic means. It does not mean that the operation itself is lock-free. So lock-free means that it's atomic, and also inside the operation, it's not going to block. So it's a stronger term. And actually, this is important, because remember that you can initialize std atomic with any type that is trivially copyable. But your hardware might not support atomic lock-free operations for that type. So for example, typically I actually have a slide about this. So atomic might not be lock-free, and that really depends on whether your hardware architecture supports lock-free operations for that type. So most platforms like laptops and phones, they support atomic lock-free operations for 8-byte types, like an int or a pointer or a size t. Some of them support operations for 16 bytes as well. Some don't. I'm not aware of any architecture that supports atomic lock-free operations for larger types. So it really depends on the type, on the tablet parameter of t. And this is why std atomic has a member function to check for that. So it's called isLockFree. And if you just call that thing for different template parameters, then you're going to see that on a typical Intel platform or like an ARM platform, like a phone, it's going to be lock-free for bool, int, double, size t, pointer, because your hardware supports atomic lock-free operations for all of those types. If you have something like std complex double, it depends. For example, on my MacBook, this is going to be true. So apparently it supports 16-byte compare exchange. On a PC that I tested, it said false. So it really depends. And if you have anything bigger than that, then pretty much all the time it's not going to be lock-free. And what atomic is going to do is it's going to, if you instantiate the template with some type that's not supported, it's going to silently insert locks inside the store and load and all these other member functions. And you're not going to even know it if you don't check. So it's going to silently support locks, and your atomic is actually going to not be lock-free. And you won't be aware of it if you don't know and if you don't check. And the really annoying thing about this is that this member function is per instance. And this has a really obscure reason. I think on some platforms or on some obscure hardware, there's like certain pieces in memory where these atomic things go. And if you run out of that space, then all other instances are going to be put elsewhere, and then it's not going to be lock-free. I don't know on what platform that's the case. Certainly not on any platform I'm familiar with. But it's a possibility. Therefore, in the standard, this thing is per instance, which is really annoying. Since C++17, it got much better now, because finally we have this one, which is always lock-free, and that's going to tell you whether that's going to be lock-free for every instance. And this function is not only static, but it's also const expr. So I'm really happy we got that into the C++17 standard. Very, very last bit about atomic is that there is this memory order thing, which is basically another parameter at the end of all these operations like store and load. You have like an extra parameter, which is the memory order. That's the other part of the C++ memory model that I didn't show. Well, if you just omit that, which is what I'm going to do for the rest of the talk, it's going to use this one by default, which is sequentially consistent memory order, which basically means if you execute different atomic instructions in a certain order, then all the other threads are going to see them to be executed in that order, which is basically what everyone would expect anyway, right? The reason they exist is that if you can sort of relax those guarantees if you use any of the other memory orders, and it's going to achieve two things. On some platforms, you can squeeze a little bit more performance out of your Lockfree algorithms, and the other thing is that it's going to become extremely hard to reason about your code. I think 99% of the time, people don't need to worry about any of this stuff. But if you do want to know more about this, I think just after this talk, there's going to be a talk by Frank Birbacher, who's going to talk about atomic memory orders. So if you want to know, I'm really looking forward to this talk. And if you want to know more about memory order, just stay in the room. But we're not going to worry about this here. Right, let's write some Lockfree code. Very simple example, we have a float, which is some kind of parameter, and we want to exchange that parameter between two different threads. And the simple example, I'm going to give an example from audio processing, but you can easily come up with an equivalent example in any other kind of industry. So what we have here is we have a GUI thread on the right, which is controlling your user interface. And you have some kind of knob there in which you can control the volume of the sound. And that's just going to be like a floating point number. And then you have another thread, which is the real-time thread, where it's going to use that number in a computation that actually computes the sound. So here's the code. Don't worry too much about it. The point is that you have this float level parameter, and then you have one thread, so whenever the user turns that knob, you're going to get a callback here, and you're going to change the value, and then in the other thread, which is the real-time thread, you're using that value in this loop to compute your audio signal. And if you write it like this, of course, you have a data race here. And the easiest way to fix this is to make this atomic. And so basically, you store the value in one thread, and you load it in another thread. And you typically have these pairs of like store in one thread and load in another thread. And this is a very common pattern. If you have this in your code, you probably got it right. We will see this again later when we implement the Lockfree queue. However, there's one thing here. If you just replace the float with the atomic float, there's one thing that you need to be careful with. So with this code, this load is going to be probably very inefficient, and perhaps you even get a different result. And the reason for that is, remember, an optimizer always assumes that you don't have a data race in your code. So if you go back to the racy version, so you have this level down here in the real-time thread, and the optimizer assumes that you don't have a data race. So the optimizer can assume that this level is not going to change while you're in that loop. So what it's going to do is it's going to probably optimize it in such a way that it's going to load the value of the level once into a register, and then it's going to use that value inside the loop. So you're going to have only one memory access, and then the value is going to be in a register. It's not going to change. And the optimizer is allowed to do that because the optimizer always assumes you don't have any data races. Now, if you do it with atomics, then the situation changes because every load is going to be actually like a hardware load from that memory location. So first of all, you're going to get 100 loads instead of one load, which is going to be much slower, especially since they're atomic loads. And then also, actually, the value can change in between while you're in the loop, so you're probably going to get a different result. So you have to do this optimization manually, where you load the atomic value once, you put it in a local variable, and then you use that inside the loop. So these are just the kind of things that you really need to be careful with. But as long as you're dealing with like floats or ints, this is really straightforward. But what happens if you want to exchange an object between threads? And then it gets a little bit more nasty because, of course, you can, if you have like any kind of struct or class widget, and if it happens to be trivially copyable, then you can instantiate it like this, but that's not going to be lock-free because Atomic is going to insert locks inside. So the thing that you can do is you can instead have an atomic pointer to that object. Now, we have a row pointer there. This should already make you a bit suspicious. So let's see where this goes. So first of all, of course, we have to initialize it. And now let's say we have one thread and we want to modify that object. But if you just modify the object and there's another thread using it, you're immediately going to have a race condition, and you can't put locks around it. So what you have to do, if you want to modify the widget, is you have to allocate a new object on the heap, and then you have to do all the setup for that object. And then once you're done, then you have to atomically swap the pointer to the old object with the pointer to the new object. And that's going to publish the change to the other thread. And then what exchange is going to do is it's going to return the pointer to the old object, and then you have to somehow dispose of it. And in the other thread, if you want to use that object, you need to get a pointer to it. But the problem is, if you just get the pointer and start using it, again, you have a race condition. So what you need to do is you need to, again, swap the pointers. And you can, for example, swap a null pointer in there. And that's going to indicate to the other thread that, OK, this object, like another thread is using that object. So there's no object in the atomic at the moment. And then you can do your work with current widget, and then you again have to dispose of it. There's several problems with that. One problem is that obviously you have to add some kind of lifetime management to this for your objects. So in C++, so you can, for example, use shared pointers. In C++ 11, we have special atomic load and atomic store functions for that take a pointer to a shared pointer. So that's an interface you can use. It's a bit ugly. In the concurrency TS, we actually have a class called still atomic shared pointer, which is going to make it nicer. So I really hope that this one's going to get into C++ 20. And the other problem is that if one of those threads is a real-time thread, you don't really want to deal with allocating and deallocating memory anyway, because that's going to be a blocking operation. So there's all kinds of techniques for that. For example, instead of deallocating an object, you can throw the pointer in some kind of garbage collector bucket, and then that's going to deallocate it on another thread. So there's all kinds of techniques to sort of manage the lifetime. And I'm not going to talk about this here. I have to defer you to this other talk I gave a couple of years ago, because that's where I'm discussing all these techniques in detail. And I'm actually showing some code to deal with that stuff. And I don't want to do this here, because I think the problem of lifetime management is very important, but it's really an independent problem. And what I want to talk here about now is the actual Lockfree algorithms. Yes?
That's the previous example.
Yeah.
You have to modify the widget, but you build the new one.
Yes.
And you should be able to read the properties of the old one.
Well, yeah, as long as you're just reading, you're fine. But if you can't write to it, so you have to write into another object and then atomically swap the pointers. If no thread is writing to the object, then you're fine. But that's like trivial anyway. What you want to do is you want to modify the object, and you can't do that. You have to set up a new object and then swap the pointers. But the whole point of this is actually that this whole idea is not actually as useful as you might think, because you can't just share an object between threads in a Lockfree way if one of them is writing to it. Because you have to sort of swap it in and out all the time. So you have to sort of push and pop it, right? And you can't just keep it. You can't keep a pointer to the object in the atomic variable, because that's gonna race, right? So at this point, it's actually better to introduce a proper data structure that deals with it, which is much more flexible. And yeah, this brings me to the Lockfree queue, because this is a very, very useful data structure that's solving all those problems. There's many, many use cases for this. So if you have a Lockfree queue, you can pass jobs to another thread. You can post parameter changes. If you have a stream of incoming data, then you can pass that on to the other thread, and you can get it out again. It's really it's kind of Swiss Army knife of Lockfree programming, this structure. It keeps coming up over and over again in many, many different use cases. So yeah, in the rest of the talk, I want to implement the structure, because First of all, it's very useful, and second of all, it shows a lot of the typical kind of problems that you run into if you write log-free algorithms. So actually, one thing I want to say about this is I don't actually encourage anyone to write their own log-free queues or log-free structures, because as you're going to see, it's a complicated business. So you should always use, of course, if you can, third-party solutions. Like Boost has a Boost log-free library with several containers in it. In Juice we have an atomic queue, atomic FIFO class as well. So of course you should prefer third-party implementations. But the reason I want to do this here is because it is very useful to learn about how to build those things. So it's really useful if you want to sort of see the typical problems that come up if you deal with log-free code. Any questions at this point? Okay, let's dive in, because this is really the fun part. So log-free queue. So what's a queue? You have a writer thread and a reader thread, so they're going to point to some memory, and then the writer can push items into the queue, and then the little x's are actually valid objects that are in the queue, and then you have a reader, and you can pop them off again, right? And so the whole thing sort of moves through memory like an earthworm, maybe. And the simplest case is single producer, single consumer, which means that you always have one thread that's pushing and another thread that's popping. So we're going to start with this, and I think we're going to have enough time to discuss the multi-consumer cases later as well. So the complexity increases quite rapidly if you do this. So let's start with the single producer, single consumer case. Right, so let's write a log-free queue. So this is the simplest interface you can possibly come up with. You have a push method and you have a pop method. So for the pop one, I use an in-out parameter that's really arbitrary. In C++ 17, I could probably use a std optional instead. So basically, and the bool is whether the pop succeeded or not. So if the queue is empty, it's going to return false. If the queue is not empty, it's going to return true, and it's going to put the element in there. And then the push adds an element to the queue. Of course, you can't just use std queue, right? We have specific requirements. So our requirements is no data races, no allocations, and no locks. So first of all, let's talk about data races. So if you have single producer, single consumer, that's actually quite simple, because if the queue is empty, then the writer and reader point to the same object, but there's nothing to read. So there's not going to be a race, because no one's going to try to read something that's not there. And whenever the queue is non-empty, the writer and reader point to different points in memory. So you're not going to have a race there, because you're not going to write and read to the same location. So no data races, easy. No allocations. And that means our queue is going to be of limited capacity. So it's not going to be like a vector where if you keep adding items, it's going to just allocate new memory. We can't do that. Because if in a real-time environment, you want to have to allocate in order to push something, we don't have time for that. So we're going to have a fixed capacity. And it turns out that the best way to implement this, and the way it's implemented most of the time, is by using a pre-allocated fixed size ring buffer, or circular buffer, as people call it. So this is the reason why this structure goes by all these different names. People call it log-free queue, log-free FIFO, atomic circular buffer, atomic ring buffer, whatever. But it all means the same thing. Basically, you have a ring buffer like this, and again, you have a writer and a reader. And if they point to the same position in memory, it means that the queue is empty. And then the writer keeps pushing things to it, and then it's going to move. And then the reader pops them off again, and it's going to move as well. And it sort of wraps around like this, and you just use this fixed amount of memory. And it's really important to notice that whenever the queue is empty, they're going to point to the same location. And now we have different choices, design choices, of how you want to implement this. And the way I'm going to implement it here is that if the queue is full, it's going to be like this. So basically, we need to allocate one more element than we actually need, so that we can use reader equals writer as a condition for is the queue empty. And if the queue is full, we're going to be in this state where the writer has sort of caught up with the reader, but there's like this one space in between. So we need to have this like extra slot in there. There are other strategies to do this. Instead of allocating this additional one, you can have like reader equals writer to mean either empty or full, and you can keep like an extra loop count to distinguish those cases. So there's all kinds of different ways to implement this, but this is the simplest way to do it, because you can just say reader equals writer means the queue is empty. It's going to make things much simpler. Okay, any questions on what we're trying to implement here? Okay, cool. So let's dive in. Let's go. These are the two methods we need to implement. And I'm using because the size is fixed anyway, I'm going to use the size as a non-type template parameter up there. You don't have to do that, but that's just the way I do it here. So first of all, we need to have the actual size of the memory. Now, I already said it's going to be one element more than we need. So we have this ring buffer size, which is going to be size plus 1. And then we need to have some actual storage. Oh, by the way, it's going to be a lot of code now, so if you have any questions at any point, feel free to interrupt me. We're going to allocate some storage for it. I'm going to use a std array. So that's going to be our ring buffer. And then we need to have a read position and a write position, which are those pointers. And I'm going to use, because they're going to be accessed from the two different threads, so I'm going to use an atomic for it. And instead of pointers to the actual memory, I'm just going to use indices into the array. And we're initializing them with 0. So that's the initial state. Everything points to the beginning. They're equal. The queue is empty. So that's all fine, right? Cool. Let's implement the pop. So first of all, if you want to pop an element, what we need to do is we need to figure out where the reader and writer positions are. So we're going to load them from the atomic values, the reader and writer position. And then if the queue is empty, there's nothing to pop. So we're going to see if they're equal, and if they're equal, we just return false. There's nothing to do for us there. If they're not equal, we have to actually pop the element, which means that we can go into the ring buffer, move the object out of it, and then move it into the reference that is given here as the in-out parameter. And then what we're going to do is we're going to store. We have to increment, so because we just read an element, so we need to increment the read pointer by 1. So we're going to increment it and store that value. There's one problem with this. We have a circular buffer, right? So at some point, if it reaches the end of the array, it has to wrap around. So we can't just keep incrementing it. So what I'm going to do instead of the increment, I have this get position after method, which checks if we reach the end. And yes, there's a question?
Yes, I'm not sure. In pop, in between loads, there's a chance of changing the situation, isn't it?
Well,
so you first load, and then you compare, and in between comparison and loading, the situation may change. Am I right?
well, so hang on. So we have one reader here.
Okay.
That's the first step. We have a single reader, so it's not. We are the only thread who's going to change that, so we're fine. We just have to see where the reader is at the moment, and then we're the only thread who gets to advance it. So you're fine. Yeah, instead of just incrementing it, we do this kind of check. Did we reach the end? And then we're going to wrap around back to 0. Again, there's different strategies how to do this. There's a way to implement this where instead of doing this thing, if the size of your buffer is a power of 2, you can just keep incrementing the pointer and not using the higher bits. So that's a little bit of optimization that some people do, but it's just unnecessary complexity here. So let's just use this. Yeah, and we're done. So that's the pop method. It's all fine, right? Let's implement the push method. Again, we need to load the write position. So we're going to load the current write position, and then we're going to see, OK, we need to advance this. So what's the new write position? So it's like increment or maybe wraparound. So we have the old and the new position, which is just the next one. And if the new position would hit the reader, right, it's like this kind of thing where the writer would sort of like overtake the reader and they would become equal. And we can't have that because it would mean that we would exceed the capacity of our queue. So if the next write position would be equal to the reader, it means that we can't actually push anything, like the queue is full, which means that if that happens, we just return false and we don't do anything. Everything clear? Now, if the new write position is not reader, it means that we have some space, so we can actually push a new item into the queue. So let's do that. Let's copy the new element into the queue, or maybe you can move it, and we atomically store the new write position, and we're done. And that's it. That's the Lockfree queue. That's not really hard, is it? OK, that's cool. By the way, the assumption here is that the copy and move constructors of the element are not going to do any funky stuff like allocating memory or anything like that, because if they're going to block inside, then there's really no point doing this, because it's not going to be lock-free. So the assumption is that this is some kind of type that it's not going to allocate memory if you try to move or copy it or anything like that. Now, this might look like a race here, right? Because you're reading and writing to the buffer, but actually it's not a race, because you're never going to read from a position and then write into the same position simultaneously, just because of the way the pointers work. It's never going to happen, so that's not a race. So this is great, and it's actually not only lock-free, it's actually wait-free as well, because if you look at this, at no point would you have to sort of like say, OK, I can't do this right now, I have to like try again or whatever. There's no such thing in the code. So if the queue is full or if the queue is empty, you're just going to fail immediately. And if the queue is not full and you can push, or if the queue is not empty and you can pop, you just do it immediately. It's like basically one operation, and it's never going to fail. So it's wait-free. That's like the best case you can have in Lockfree code. Cool. Easy. There's a question?
I have a question. Is it guaranteed that if the buffer is regular memory, that by reading and writing adjacent objects, there will not be some kind of cache line with issue where you think you are writing 10 bytes to the buffer, and actually you are overwriting, you are writing 16 bytes and you are overwriting 6 bytes of the next slot in the array with something that was there before but has been changed by other thread already.
So basically the question was, can you run into problems with cache lines?
Yes.
Yeah, so this is another problem which I'm not talking about. But of course, if you, so the way data is shared between threads is in cache lines. So if you're going to write to a piece of memory and you're going to read from an adjacent one, so the write is going to invalidate the whole cache line. And then you're going to have something like locks on the hardware level, where before you can read from the same cache line, you have to actually fetch it from memory again. So it's going to invalidate the copy in the cache from the other. If it's on another core, it's going to invalidate that cache, and it has to read the whole cache line again.
Okay,
so yes, it would happen. It can happen, but that's like a whole other problem.
But it is guaranteed that it is only going to be a performance hit, and it is not going to cause wrong behavior.
Oh yeah, it's just the worst thing that can happen is you can get a cache miss on the other core, and then you're going to have to refetch that cache line. Okay. So yes, that can happen. If there's ways of getting around that as well, which I'm not going to show. But in this very, very simple example, yes, it can happen that you're going to get a cache miss because the other thread modified an adjacent piece of memory, and then you're going to get a performance hit. But that's the worst thing that can happen. Unless you have some really weird stuff with like misaligned memory or whatever, which we also don't have here. So yeah, no problem. Another question?
So if your reader is running slower than your writer so that the buffer ends up getting full, what kind of strategy do you use at that point? Because at that point you're actually going to be failing on your push a lot of the time.
If the question was, what happens if your reader is slower than your writer, and then your queue is getting full, and you can't pop items anymore because you can't push items anymore because the pop is too slow. The answer is, in practice, there's different ways to deal with this. The simplest way is to increase the buffer size, which is what we do in practice. Another way is to do like a slight modification of the structure where it really depends on what you want to do. So you can modify the structure in such a way that if you keep pushing, instead of failing, you just keep overwriting the oldest. So you keep overwriting the oldest element. So it just keeps going round and round and round. If you pop, you're just going to get the newest one, and the oldest ones just getting silently overwritten. That's another thing that you can do in practice. It's very easy to modify this code to do that. So that's another strategy. And it really depends on whether you can discard the old values or whether you cannot discard the old values, because you have some kind of stream of data where you need to get every single element that has ever been pushed. And then you should instead increase the buffer size. But there's different strategies to deal with that. I should say that this is the most simple case. There's if you encounter these structures in practice, there's hundreds of variations of how you actually implement them, or how do you add to this code, depending on your use case, to deal with all these kind of cases. Okay, shall we continue? So we have this. Yeah. So we now have just this interface here, and of course, if you want to do this, if you're writing a library class here, there's a lot of things that you can add. For example, you can add a push that takes an R value reference, so you don't have to copy it. You can add utility functions to it, like size and clear, like the usual container stuff. And then another really useful addition is to push a whole range of elements, or to pop a whole range of elements, and you get a pair of iterators, and you're going to push the whole range into the queue. Or you can pop all the elements and put them into an output iterator. Yes, question?
Why do you pass the iterators as a pointer?
No reason. OK, ignore the star. Yeah. The question was, why do I pass the input iterators as a pointer? Forget about it. I think the original version, I was passing row pointers, and then I replaced them with iterators, and I forgot to remove the star. So just ignore the star. Yeah, sorry for the typo there. So anyway, so you can add these utility functions. And push range is really useful if your elements are integers or floats, and you have a whole chunk of them, and you're just going to... Yes, another question?
Yeah, the push operations should require a return type that returns the last push input iterator, because you might not, and you might not know how many you actually succeed with pushing.
So the comment was, if you push a range, you should return some kind of value that indicates how many elements you have actually pushed. Great, that's a great idea. Yes, you should do that. Basically, the whole point of the slide is you can keep adding those utilities and those useful things, and eventually, if you keep doing this, you end up with an interface that looks like a proper library implementation if you do all those things. So this is now almost like the interface of Boost. Boost Lockfree has the SPSCQ, which is basically that structure. And if you add these kind of methods, then it's going to look very much like that structure. So yeah, you can sort of refine that interface and add all those things, and then it's going to become a proper library class. But we're not going to do that here, but yes. So yeah, we're done. The single producer, single consumer case is completed. And we do have a lot of time left, so we can actually talk about multiple producers and multiple consumers. And this is where it gets really, really fun. The first question is, again, why would you even bother doing this? And I think my opinion is that if you can write code with single producer, single consumer queues, or if you can rewrite your code so that you only have one thread reading and one thread writing, you should always do that, because it's going to save you a lot of pain. But sometimes you can't do that, because obviously we have multi-core platforms, and you want to use those cores. So you want to distribute your work among those cores. And one of the situations you might end up with is that you have different processing threads that do some number crunching on different cores, and then you want to get all this data into your real-time thread, and then you want to get it out again. And so either one direction or both of them, depending on your use case. And you want to push data from multiple threads into a real-time thread, and you want to push it from there to multiple threads as well. So in those cases, you need a multi-producer queue or a multi-consumer queue or a queue that does both. So we don't have time for the multi-producer queue because it's a bit more complicated. So in this talk, I'm going to just talk about the multi-consumer queue, but maybe I can do the multi-producer queue next time. It's a lot of fun. But yeah, let's talk about the multi-consumer queue. So let's have the code that we already have, and let's see if we can just modify it a little bit to allow for multiple consumers or multiple readers. So what do we have to modify here? It's going to turn out that it's actually not as bad as you would think. So first of all, this line is a problem, right? Because another thread might also be reading it, and if you're moving it out, then the other thread is going to read garbage. So you can't move it, you have to copy it. But again, like reading from the same location from multiple threads, it's okay. So if you copy it, you're fine. As long as the copy is not going to do any funky stuff. The next problem is this gap here. Because what you're doing here is if you read the element and then you're updating the read pointer. If another thread is also reading it, it's going to be finished. It may be finished before you, and it's going to update the read pointer while you're still somewhere before that red line. And then you're going to run into a problem because you're going to, by the time you get to, so after you copied the element, you want to update the read pointer, but by the time you get there, another reader has already updated it. So you need to fix that. And the way to fix that is, as we already saw earlier, compare exchange is really useful to do that. So we can do this, and you can say, OK, I've read this value, so I'm fine. I want to advance the read pointer, so I'm going to ask, is the read pointer still the same as when I was reading it? Or in other words, am I the thread that's going to get to update the read pointer now? And if that's true, update it to the new value and return. Right?
And if not?
And if not, you have to read again. If that fails, basically, then, oh, someone else changed the reader position, so you have to load it again, right, because it has changed. And then the element you read, another thread has already read it before you, so you have to actually try the whole thing again. So you're going to put all that stuff in a while loop. Yeah, so you read an element, and you try to advance the read pointer, but, oh, someone else has already read it and already incremented the read pointer. So discard it and try again. OK? Is that code correct? Yeah?
I don't think so.
You don't think so? OK, I'm going to give you a hint. There's a bug here. OK, so this is a great example for how it becomes really difficult to spot those race conditions. Actually, this room is really good because a lot of hands went up. Yes? Yeah, we're going to come to that. OK, so here's a bug. And the bug is, OK, let's say we have one reader which is reading this element, and then another reader which is also reading the same element. And then the other reader gets to do the compare exchange. Now, there's like one case that can occur here, which is basically, so you're trying to read a value. Another thread has already read this value. So you're in this loop, and it has failed. And then why you did that? So the thing here is, if you want to spot those things, you need to assume that, or basically imagine that any line of code can be simultaneous with any other line of code. And any line of code can take any amount of time. And also, your whole thing can be in any state. And so it's a bit tricky sometimes. So basically, you failed to read this value. Another one has read the value. And then while it was doing that, actually, the writer has pushed a lot of new items into the queue. It's gone all the way around. And it's going to try to, so the writer has filled up the whole queue while you were stuck in this one line. And now it's going to write into the same piece of memory from which you're still trying to read here, if you're reader one. And then you're going to have a race here where the writer's writing and the reader's reading from the same memory location. Yeah? So congratulations, you've just opened the gates of hell. This is the kind of stuff that you need to deal with. So how do we fix that? It turns out, some people say it's actually not that bad, because if you have in this case where the writer writes and you're still reading from the same memory location, it's actually fine. I mean, you're going to read some junk, but in the next line here, you're going to realize that you have read some junk. So you're going to anyway discard it and try again. So yeah, you're going to read some junk, but it's actually fine, because you're not going to use that, which is true on certain platforms, like Intel, probably, because that's the way Intel works. It's going to be atomic anyway, maybe or maybe not. What about ARM? I don't know. What about if T is like not a float, it's like a big object, and is it still going to be fine to read some? Okay, so actually it's undefined behavior, so you can't do that. And yeah, if you care about portable code, you wouldn't rely on the fact that if you read kind of junk and then you discard it, then that's okay, because it is actually undefined behavior. So we need to fix that. And unfortunately, in this case, there's no easy way to fix this, because you can't put a lock around the memory access. So what you need to do is you need to make the memory access itself atomic now, like to the actual data. So instead of having our ring buffer full with T's, we need to have a ring buffer full with atomics, so that the actual access into the data is going to be atomic as well. Which means, again, that if you want to store something that's not an int or a float, but you're going to store objects in your queue, then you have to store pointers to them, and you have to deal with the lifetime. You have to write some code around it to deal with the lifetime, because the only way you can access data simultaneously, writing and reading, without locks is atomic, right? So that's what you need to do here. So you need to, instead of just reading and writing, you need to have atomic stores and loads into the actual data, which fixes the problem. Are we good? So we don't really have to modify this code at all. We just need to make sure that the access into the actual data is now also atomic.
So
Yes, that's the question.
The elements read from this queue should be in the same order, right?
Yes.
If the writer arrives to fill it, isn't the reader going to read elements out of order?
The question is whether the reader is going to read elements out of order if the writer overtakes it, or no? Why would it do that?
Because if the writer happens before the reader, you load something that is new, right, in the same position.
Yeah, but then you're going to realize that, and then you're going to try again.
Okay, you discard it after.
Yeah, so if something went wrong, then this is going to return false, and then you're going to discard the whole thing and load the read position again and just try that again. But actually, there is another bug here, which I think you've sort of spotted. Yeah.
I was wondering, because while true, you changed the old read post, but you only checked once with the original version against the write position, so you overflowed the
Very good. You discovered one more bug in this code. So, yeah, you want to say something, or?
I think you can also have an infinite loop if you have two concurrent readers on a buffer where only one element is left. Then both of them try to read it, one gets it, and the other one goes and tries again. And there is nothing more, and there is nothing more, and there is nothing more. So it will loop infinitely. It doesn't fail like it should, but it keeps looping until
Yes.
somebody has
So
stuff to the buffer.
you describe the same bug in different ways. So there's one last bug here that we need to fix. And the case here, what can happen is that if you're in this situation, for example, where you have one item left and both readers try to read it, and then obviously one of them finishes first, and then the queue is empty. But then the second reader is still trying to read it, right? So both readers are in the green line of code here, and then one reader succeeds and the other reader is still there. And what happens is it's going to read it, it's going to realize that the other reader was faster, and it's going to load the new read position and try again. But the problem is that the queue is now empty, and there's nothing to read. But it's going to just keep trying to do it, even though there's nothing to read. And that's the other race condition here, which means that our dragon just grew like a new head, and we need to deal with that. So how do we fix that? Well, basically the bug here is that the compare exchange is going to correctly tell us the read position has changed, and then we load the new one, but we don't check if the queue is actually empty now. So this is the code that checks if the queue is empty. And what we need to do is we need to move it into the loop, right? And if we do that, then actually this one becomes obsolete. We can get rid of that, and now we're done. And that's now correct code. And actually, it's shorter than the first buggy version. It's almost as short as the produce a single consumer one. So that's going to work now. And it looks like this large while loop. This looks a bit scary because it looks like the pop could get stuck in this loop for a while, a bit like as if it was blocking. But actually, it's not blocking, because if the loop fails once and you have to do it again, it means that another reader succeeded in reading. So it means that the other readers have made progress. So it's this case where it's lock-free but not wait-free. But it's still lock-free. And you could imagine a theoretical case where like one of the readers is just going to be very, very unfortunate every time and just going to be stuck in that loop while all the other readers make progress. But in practice, that's a very unlikely case. And actually, the probability for that to happen goes down exponentially. So yeah, so that's a lock-free multi-consumer queue. There's one question in the back.
How about the case where you break between reading write cost and read cost, and then the points compare equal, but actually the queue is not empty, so this code would not read from a queue that contains elements?
I'm not sure I understand the question.
So suppose you have queue.
You want to come up here and show me the line of code?
So suppose you have a queue with a couple of elements in it,
Yeah.
and then you arrive at this line,
Yeah.
and you capture the right position.
Yeah.
And then your thread stops executing,
Yeah.
and some other threads keep on working with the queue. Read all the elements, and the writer keeps going,
Yes.
and then it's your turn again, and you get the read position.
Yes.
And then it happens to be the same as the old write position, but the write position has
Yeah. This
advanced
is
in the
why.
meantime, right?
This is why.
And then you pretend,
Oh.
the queue's empty,
Let's
and
let's
go
let's.
not do anything, but actually there are elements in it.
I'm not sure that's a problem, but I think we need to sit down and work it out.
Sure.
Yeah, interesting. It's not really easy to reason about this stuff.
Yeah.
I'm not sure we can fix this in 1 minute or like figure out if that actually happened.
Probably.
I don't really see it, but let's sit down after the talk and like go through it properly. Is that okay?
I appreciate that you say it's hard to do, so.
Yeah. So basically the takeaway message from this talk is it's really hard, you shouldn't be doing it, just use a library implementation.
Are you sure the library cares about wrapping around correctly?
Well,
Fairness?
our library cares. And yeah, I don't know. Any more questions? Yeah?
Why continue the marketing? Why don't just replace all write costs in the if statement with just loading directly
The question was, why don't I replace these with just loading?
only the old write?
Because we're going to use it again later. No, we don't. Yeah, we could do that. So we can't replace this one because you're going to use it again there. Yeah, we could, instead of writing this, we could do load here, yeah. It's just cleaner this way. I like having loads and comparisons because they're different things. I like to have them on different lines.
Print something
Yes?
It could even be nicer in C++17 where you don't have the while true by introducing old read pos.
Are you referring to the feature in C++17 where you can initialize stuff in the if? Thanks for that comment. I love that feature. Yeah, in C++17, you can if, and then you can initialize the write pos here and the read pos and whatever you want, and then do the comparison in one if.
I would do it in the while and use the read pos and just use write pos load for the
Can you, hang on. You can't initialize stuff in the while loops. This feature works with if and a switch. As far as I know, it doesn't work with while.
And then use for.
Yeah. Okay, yeah. So there's ways of writing this code in different ways. I think it's reasonably clean, but obviously
So
you can.
do it now with for.
Yeah. You can massage this code to make it look different, but I think it's reasonably clean to sort of get the message across. But yeah, you can.
A while true is always suspicious.
Yeah, you can write for semicolon if you prefer that.
Well, the for loop can take the condition to.
Yeah, sure. Yeah. Okay, but it's not changing the algorithm, right?
No.
So it's just coding style.
Nicer.
Cool. Any other questions? Yes?
Is there any way to prove that it is correct?
The question is an excellent question. Is there any way to prove this is correct? And I assume you mean mathematically prove. Not that I'm aware of. So this code is complicated enough that I wouldn't know of a like rigid logical framework where you could sort of like prove it mathematically or something like that. I don't think that's possible.
You would use CSP or process calculus, surely.
Sorry?
You would use communicating sequential processes or process calculus by Milner. That's how you prove these things correctly.
Okay, that's a great comment. Do we have a mic bowl here so you can say that again and it's going to be on the video? Because I'm not able to repeat what you just said. But yeah, you're basically saying there is a framework which you can use to prove these kind of things. Okay.
Hoare.
Sorry?
Tony Hoare.
Okay,
Communicating sequential processes.
cool.
CSP.
I'd love to hear about that stuff. Let's talk about it later.
But it gets more interesting if you add memory orders to loads, not sequential consistency.
Can you please repeat into the mic? We have a mic now.
Oh, yeah. So the first answer was, can you prove is that I can't, but I know there are mechanisms, and the colleague told about communication sequential processes, CSP. It's an old model by Tony Hoare, and you might end up finding something. And I didn't understand the other thing.
Process calculus is an equivalent
Process calculus?
by Milner, yeah.
Okay, so there might be means to prove things.
This is why I
And-
love conferences. You learn
And
so
my
much new
comment
stuff.
was, if you add memory order that's not sequential consistent to the loads and stores, things get much more interesting and much harder to prove.
Oh, yes. And this is why I'm looking forward to the next talk. So I completely ignored the issue of memory ordering because this is all just sequentially consistent. But it gets much more interesting if you want to optimize it further and you use like relaxed memory order and things like that. It's going to get even harder to reason about the code, which is really, I didn't have time for that stuff in the talk. But I'm really looking forward to the talk that's just going to be just after this. So yeah, it gets much more interesting if you do that. More comments? Can you please all use the mic from now on, because we have a mic now. Is that okay if you just
I'll bring it to
pass it around? Thank you very much.
Thanks. I have a question about the atomic ring buffer, which is atomic now, but not in the single producer, single
Yes.
consumer scenario.
Yeah.
Why is it not required to store atomic keys in the single consumer case? Because we have atomic access to the write position and the read position, but is there any guarantee that the reader actually also reads the correct value that the writer inserted into the queue?
Basically, the question is, why is this not a race condition?
Yes, why is this not a problem?
Because there is no state in which the object can end up where read and write position would be equal, and you would also be executing pop.
But isn't the optimizer allowed to swap the assignment into the ring buffer and the store into the position?
Well, you have atomic operations here, right? You have load and store, and we use sequentially consistent memory, so it's not allowed to move everything So whatever is under the load, the optimizer is not allowed to move it above the load, and the same for the other one. Like yeah, there are some if you use, it's again this kind of memory order stuff, there's some certain restrictions on the optimizer what it's allowed to swap. And if you have an atomic load, it's not allowed to put things that are under it and put it in front of it.
Okay, so it's the important thing is to have the store after the write into the buffer. Otherwise, we would
yes,
break
exactly.
the queue.
If you swap around and don't want to fall in there, oh, I have a laser pointer, yay. Yeah, I just bought it yesterday, so I'm not familiar with it yet, but it has a laser pointer. So if you put this in front of that line, you don't have that guarantee anymore, and then, yeah, you're going to have a potential race condition that's going to screw it up, yeah. So the whole point is that, yeah, because, yeah, exactly.
Thanks.
One last question here.
Suggestion actually. Next time the line of codes in the
Sorry?
the lines.
Can you speak into the mic, please?
No, I mean I have a suggestion for next time. If you add the line of codes in the code, people can refer to the lines without falling down.
That's a great suggestion. I'm going to do that from now on. I'm going to have lines, code, yeah, line numbers, yeah. Thanks. I'm going to adopt that. Thank you.
Hi. It's a practical question because your advice from the beginning of that talk is essentially don't do it yourself. Well, fine, and I see why. Wouldn't it be acceptable, I don't know, sacrifice to, instead of juggling, in this case, two pieces of log-free atomic data, to pack them into one, and then sacrificing size of that, in this case, this circular buffer, so pointer can only occupy half of atomic, well, integer in this case, just collapse all those obscure corner cases we are discussing from last few minutes to none. Well, so you would have one load and one store instead.
Well,
instead
remember
of two.
that typically you only have 8 bytes to work with if you have an atomic variable.
So would you say that you need 8 bytes size of addressing of circular buffer?
No, but you have some, okay, if you are storing integers in the queue, and then you don't need to exhaust the whole range of the integers, so you say, instead of storing integers, you're going to store like shorts.
Yes. No, this is not what I'm saying. I'm saying that positions are, instead of integers, are shorts.
Yeah,
but what you store is up to you.
Sure, the positions can be shorts, yeah.
Yes.
But that's not going to change anything. What you want to do is you want to...
No, you can load them both at once and store them also at both at once.
Oh, that's interesting. So you're suggesting to pack the reader and writer positions into a single atomic variable.
Yeah, it looks to me like a lot of those bugs you just discussed just wouldn't be there in the first place.
That's a good idea. I actually think people do that.
Okay.
I think there are implementations which do stuff like that.
Okay.
I remember Tony van Aert does these talks on Lockfree structures. I think he has a few talks where he's showing tricks like that. Yeah, people do this kind of stuff. Oh. And actually another comment, if you do this kind of stuff, you can't, like the compare exchange becomes much more difficult, because the way I'm using it here is you just want to know whether the reader position has changed, and you only want to know whether the writer position has changed, and that's really easy to do with the compare exchange. But you have them packed into like one single atomic variable. You need to do some like atomic like bit masking stuff, so it's going to be actually much more complicated.
Not a very good idea, I believe.
Yeah, but I've seen people doing tricks like that, but probably not quite what you suggested. But like packing things into like several things into one atomic variable, that people do this kind of stuff.
Would stood pair work?
A stood pair of what?
So if you're storing the state of the queue, as seen by one thread, saying, here's the start,
So sorry, can you use the mic, please? I can't really hear you very well.
So back to your point about not having to get into bit packing and messing around like that. If we just use a stood pair, and then his point about you could detect when you know there's been a change.
So you want to pack what into the pair? The two positions?
Yeah, read and write positions, yeah.
Well, that's exactly what you suggested as well.
Yeah, but that's simple. I agree, it's still got the same issues.
Yeah, you could pack them into a pair. It's like bitwise, it's the same thing anyway, right? It's just, you give it a different name, but.
What's your opinion with transactional memory in the game? Is going to issue this kind of stuff, or?
I think that's a topic for a whole other talk.
Okay.
I think the time is over. I'll be around for the whole conference, so I'm happy to chat about all these things. Looking forward to it. Thank you.